EEGLAB track. So we're going to go over the very basics, opening EEGLAB, importing data and pre-processing, talk a little bit about running ICA, looking at your components, that sort of thing. And I'm Julie Onton, by the way. I am a member of the lab from years and years ago. I'm not currently in the lab, but was involved in some of the early work we did with ICA. So this lecture is about data import and pre-processing and some basic ERP visualization on the channel level. So first you'll start MATLAB, which I presume all of you can do, and then make sure that you add the EEGLAB folder to your MATLAB path, and that you just do with the command add path. And you'll want to save that in your path def so that every time you open MATLAB you can just type EEGLAB and you'll get the GUI coming up. So this is the EEGLAB GUI, and this will be populated once you load a data set. So for this lecture, we have a sample data set called simple oddball.set, and this is a 68 channel, 256 sampling rate biosemi recording. The data is already referenced, but we'll practice re-referencing if you'd like. And then the task was a speed button press to a star shape, and you ignore the circles, and there's about 200 trials. So this is the basic pre-processing pipeline that we use to process EEG data primarily for running ICA. So we assume that you collected some high-density EEG data. The high density is basically 30 channels or more, up to 256 or whatever you can put on the head. So below 30 channels starts getting a little bit sketchy. You'll have scalp maps that look pretty good, but that's because it's a lot of interpolation. So that you can really identify independent sources with less than that is kind of sketchy, because you think about how many sources are in the brain and you're only getting out 30. You're mixing a lot of stuff together into single components. So you want to get as many channels as you can for ICA. So the next thing you'll do is import the data into EEGLAB. So EEGLAB has many different formats that it can import, and hopefully yours is here. If worst comes to worst, you can convert your data to something like ASCII or a MATLAB array, and you can import it that way. If you do use biosemi, we suggest using the BDF plugin that works well for us. So once you've imported the data, then your EEGLAB GUI gets populated with information about your task. So it tells you how many channels you have, how many epochs, how many frames, whether you have a reference or channel locations, etc. So it's a quick reference for lots of key information. Next in the pipeline is to import event markers and channel locations if they weren't already imported when you imported the data. So to import event info, you have a bunch of different options. Again, you can use a MATLAB array or ASCII file, a data channel, which I'll show that example, but also you can use presentation or ePrime or neuroscan event files. So if you do it from a channel, you would put in the channel number that contains the events, and often this looks like this in the data scroll. So it's zeros until you have an event, and then there's a value that's associated with that event. So EEGLAB just goes through and reads those numbers off. So if you imported the events correctly, then there should be a number here in the GUI that represents something close to how many events were in your task. Okay, importing channel locations is also in the edit menu under channel locations. And if it finds that you have standard location labels for your channels but no locations, it will actually offer up right away whether you want to import a standard location file. And so there's a few different options here. And if you do that, the GUI will come up with your location labels along with locations here. So these are just different ways of representing the location, either X, Y, Z, or theta and a radius, and you can go between the two. If you did not choose to import locations, you can read locations in. So there's 7 different formats you can use: Polhemus or BISA, LGuide, or other ones. And so that's if you actually digitized where those electrodes were on people's heads. Or if you didn't import the center locations up front, you can do it with this button here, look up blocks, and it'll give you the same GUI that you saw at first here. So when you're importing it, or after you import your channel locations, there's a few things you might want to do. This is usually only necessary when you have your own locations that you digitized. So you want to optimize the head center, and usually here the defaults are what you need. So what this does is just puts all of your electrodes around 0. So sometimes when you digitize, they're kind of all, you know, positive numbers and not around 0. So it for various reasons, it's handy to have them all around 0. So usually I just do this anyway, just to make sure they're all around 0. And the defaults are probably what you want. The other thing you can do is rotate the head axis. So so the default here is to put CZ at the top. So basically, if I'm standing straight up and I'm looking straight ahead, CZ is going to be the highest point up here. Sometimes channel locations come in sort of tilted like this, and it's like the person's looking down, and so the highest channel would be something like PZ. So this just rotates it back up, and it's just for visualization. It makes a little bit more sense when people are looking at the scalp map. Another option is to set the channel type. So this is sometimes handy if you have something like a heart electrode or EMG or some other signal in your EEG data file, but it's not actually on the scalp. So this is handy for running ICA later. So ICA will only look at EEG channels, and if you label it as something else, it will ignore it. So the type would show up in this last field. Okay, so then also from this menu, you can plot the channel locations in 2D or 3D. So this is important just to make sure everything looks right, that it's centered the right way, and they all pretty much make sense. And this can be important when you look at the scalp maps and they look crazy somehow. You can check this real quick and make sure that all the electrodes are actually in the right place, because that can happen. And you'll think that ICA was screwed up, but it's actually your channel locations. Okay, so once you've imported the channel locations, your GUI will be updated saying that yes, you have channel locations. All right, next step is re-referencing or downsampling, and this is just if it's necessary. Oftentimes this re-referencing happens right when you import, and downsampling is definitely not compulsory. It's just if you had like 2,000, hertz, and you just don't have the memory for that. So re-referencing, you have the options to do, for example, average reference. So you would click this box. You can also, with average reference, you can choose to exclude some channels. So if you wanted to not include the I channels, for example, you could do that, and you would just click on the button to the side. You can choose those channels that you don't want to include, and they would show up here, or you can type it in yourself. Or, for example, you could link re-reference to linked mastoids, and so here you would click this button instead, and you would list here the channels that you want to reference to, or you can choose it from the GUI. Just a word about the choice of reference. Of course, up to you, and sometimes there's reasons to go one way or another. There's probably no perfect reference. In theory, average reference should be good, because the outward and the inward currents, when summed across an entire sphere that's electrically isolated, it should sum to 0, and that should be ideal. But that means you need an even distribution of electrodes all over the head, and in practice, it's very rare to have electrodes at the bottom of the head. So, that's just something to think about. There's no perfect one, so you do what makes most sense for you. Whenever you change an EEGLAB dataset, and this is going to come up several times in these lectures, it will ask you what you want to do with the datasets. So first you have the option to rename the dataset or name it, this new dataset that you've created. And then you can check this box if you want to save that file immediately to disk, and so that you can check that box and browse for where you want to put it. And then to the bottom you can say whether you want to overwrite it. So Arno may have talked about the structure of EEGLAB. So all EEG contains multiple EEGLAB datasets, so capital EEG datasets within all EEG. So what this means is that the current dataset is called EEG, and then if you want to overwrite that, EEG is now going to equal this changed dataset that you've just made. If you don't click this box, it's going to create two EEG datasets, and you can toggle between them. So here, if I don't click overwrite, then I'm going to have two different datasets here. So I'm going to have a number 1 and a number 2, and you can toggle between them in the datasets menu here. And if you name them something that's descriptive, like it's re-referenced or something like that, then it's easy to know which dataset you're working on. So yeah, so for example here, this one has a different reference. And resampling, very easy. From the tools menu, change sampling rate, and then you just simply type in the sampling rate that you want and press OK, and that will downsample your data. Okay, the next step, high pass filter. So high pass filtering is not necessary when you're just looking at the channel level. It's very necessary for ICA if there was no if there's no high pass on your amplifier, and that's just because ICA can't handle slow drifts. So to do a high pass is from the tools menu, filter the data, and there's lots of different options, lots of plugins for different types of filters, but the basic FIR filter here, you would just type in what low pass or what low frequency you want to high pass over. You can also put a higher edge if you want, but I'll show you in a second a better way to get rid of line noise if that's what you're trying to do. And the high pass frequency cutoff depends on your data. So the lower the frequency, the longer the stretch of data that you're looking over to find those frequencies. So sometimes practically it's hard to go very, very low. Of course, the lower the better, so you don't get rid of actual EEG data. Okay, so again, if we high pass, we're changing the data, so it'll ask you what you want to do with the data. Okay, so removing line noise might be desirable. It's not necessary for ICA. ICA doesn't really care, but when you're looking at the channel level, it may be too distracting to have lots of line noise over it. So EEGLAB has a really good function to get rid of line noise without getting rid of everything in the high frequency range. So, and this is a plugin called Cleanline. So to make sure that you have it or to go get it, you can go to File and Manage Plugins, and then go to Manage Data Processing Plugins. And here you can find Cleanline up at the top there, and make sure that one is installed. So if you installed it, go to Tools, and then Cleanline is at the bottom, and you'll get this interface. So the defaults should work. There's a couple of parameters to consider, like the size of the window length and the step size. So the step size will determine how overlapped that window is. And then, you know, if you want to speed things up, you can not option for the visualization after this occurs. It is kind of interesting to look at the peaks that were removed. So you can set that or not. So I'll show you what it does look like when you use Cleanline versus a low pass filter. So you could look at this using channel spectra and maps or channel properties, which I'll show you. So channel properties, you can just type which channel you want to look at and the frequency range. So here we want to go above 60, so we can look at the 60 hertz peak. So here's a power spectrum for the channel right in the back of the head around PZ. And this is just with a high pass filter at 0.5 hertz. So you can see there's a huge 60 hertz peak. If you do a low pass filter, of course, it just starts angling down the power around 50 hertz. You still have a 60 hertz peak, but it's just, you know, now it's just lower than the rest of the data at the low frequencies. Cleanline is pretty amazing. So it actually just takes that 60 hertz peak and gets rid of it. So now you can still look at frequencies higher than 60 hertz but also not have to deal with line noise. So it's pretty close to magic, in my opinion. So I really highly recommend it. All right, the next step is to identify and reject bad channels. Of course, it may not be necessary if all your channels are great, but there's a few ways to find bad channels manually and automatically. So manually, you can go to plot channel data scroll, or equally, you can go to reject continuous data by eye under the tools menu. These are the same option, just two different GUI options. If you do the reject continuous data by eye, you're going to get this warning, and it's just telling you that you're going to reject the data permanently when you press reject. So this is what it looks like when you scroll the data. So there's a few options here in the settings tab. You can change the number of channels you want to view, the time frame you want to view, and whether you see the events there or not. You can adjust which second or which epoch you're looking at, so you can jump to someplace else in the data very quickly that way. These scroll buttons go either by 1 second or 1 epoch, or change the whole page. And then the scaling, again, you can see the data either as very large deviations or very small ones. It's just a visualization. These are event markers, so this is telling you this is event label 1, 2, 202, and 1, and so that can help you understand where you are in the task, what just happened. So manually, you could pull up the data scroll and see that there's a bad channel here. EEG is extremely correlated from one channel to its neighbor, so if one is just clearly not like anything else, unless it was in some weird far off location on the head or someplace else, it should really resemble other channels. So this is a pretty good indication that that's a bad channel. You could also look at the spectra, so sometimes that can clue you into channels that are bad. So here you can see, most of the channels are down here in this range, and you have a few up here, and you can tell where they are. They're up in the front left area of the head, and you can confirm to yourself that this is really bizarre by looking at the channel properties and looking at channel 3 and channel 31, for example. And so you can see again that the spectra are very different. You can also see here that the microvolt value is very different here. So we have a very strange value here. So it's another way to confirm for yourself that these are strange channels. We also have an automatic channel rejection function, and here you can tell it which channels to look over and which measure to use. So probability is a pretty good one. And when you do that, and so the threshold is a standard deviation value, so you're looking for channels that are, again, just different from all of the other channels. So this is what it looks like when it chooses the bad channel. It just highlights it in red for you. And then to actually remove the channel, you can go to Edit, select Data, and then you can either just type in the channel that you want to get rid of, or you can go to the button again and choose channels you want to get rid of. You want to check this box, because if you don't, you're going to end up with one channel. So if something weird happens, go back and remember that box needs to be checked to remove the channels that you've listed. And again, you've changed the data set, so it'll ask you what you want to do with this data set and the data set that's currently in memory. All right, so here you probably want to stop and save your data set, because this is the data set that you're going to go back to. You're probably going to keep going, run ICA, and so sometimes you get rid of artifacts and stuff, and you epoch and other things to your data set, but sometimes you want to apply your ICA weights back to an original continuous data set. So here's where you want to do that. You've gotten rid of your bad channels, and you've done all the pre-processing. So so save that. This is kind of your baseline data set. And then I'll talk about getting rid of some large artifacts. There's different ways to do it. I'll talk here about doing it after you've epoch the data. In the next lecture, I'll talk about doing it on continuous data. And then next lecture, we'll also do running ICA. So because we're going to get rid of some artifacts on the epoch level, we can do some basic plotting of channel data. So to extract epochs, you go to the Tools menu and the Extract Epochs function. So in this data set, you have event code 12201, so that corresponds to the star, the circle, and a button press. And again, the star was the non-target, the circle is oopsie, sorry, I have that backwards. The non-target is the circle, and the target is the star. So here, it's choosing event number 1, and it's listed here as well. So it's going to go through and find all the event 1s, and it's going to pull those out and put them all, stack them all together as epochs. So when you extract epochs, you change the data set again. It will always ask you when you epoch whether you want to baseline the data or not, and that just means you're going to take out the average from a period of time, any period of time in that epoch that you choose. Here's choosing the default, which is from the beginning of the epoch to time 0, and that's just pretty standard that you want to, you're saying I'm interested in this event of interest. I want to know what happens after that, so you kind of want to pull everything down to 0 first and then see what happens later. If you don't do that, you can have skewed results, because if you start at 50, it goes to 100, you might think that that peak is actually 100, but it's actually just 50 relative to that event lock. So the default is the whole baseline. You can just pull the whole epoch down to 0, an average of 0, by not putting anything. If you don't want a baseline removed at all, you have to press cancel here. And so this is what the GUI looks like after you've epoched the data. So now your epoch field should say a reasonable number of epochs. And now it'll have a number of frames per epoch instead of number of total frames. All right, so as I said before, you can save it immediately, or you can save it later from the file menu. Okay, so going back to the plotting, and so here we want to reject bad epochs, so you want to get rid of just noisy epochs in your data. So you can scroll the data again. This time you're looking at epochs. So this is 1.1 seconds of an epoch around the event 1, and then each one of these is 1.1 seconds. You can click anywhere inside one of these epochs and it'll choose the entire epoch for removal. And then if you press the reject button, it's going to take that epoch and it's going to delete it from your data. And once you do that, of course, you've changed the data, so it's going to ask you what you want to do with the data set. You can also use some automatic rejection tools that we have. So in reject data epochs here, so all methods will give you a GUI with all of these included. So that looks like this. So we've already looked at how to do visual inspection. There's 5 different tests here. The probability one is, again, one that I find the most useful, and the parameters are basically these number 5. So these are standard deviations from, like if a single channel is 5 deviations from the mean, or if all of the channels have gone off 5 deviations from what's normal. And so here you can press calculate and then scroll the data. And what you'll find is that some epochs have been highlighted for you. The automatic rejection protocol has found. And so you can click on any one of these pink ones to unmark it, or you can mark extra ones. So you might say, I don't want this one either, and you can go ahead and click on that one at that time as well. And when you're done, you'll just update marks. So actually, when you press update marks, it hasn't rejected anything. It's just marked that epoch for removal later. And you can go through as many of these as you want. You don't have to go through all of them. You just choose the ones that you like, and you can play with them. You can calculate and plot it, and go in there and unclick them if you don't like what they found. So this is a good one to play with if you are good with all the basics and stuff. Okay, so then when you're done with all of these tests, you can choose one of these 3 buttons at the bottom. So you can either close that, start at the right. You can reject these immediately, everything that was marked. You can press reject marked trials, or you can clear all the marks if you didn't like what they did, and nothing will happen in your data set, or you can choose to keep the marks but not reject anything right now. And if you choose that latter one, the way that you actually get rid of that data is to go back to reject data epochs and choose to reject those marked epochs. All right, so now that we have clean data in epoch form, we can visualize some of the data. So to visualize the ERPs, just basic ERPs, you can choose the scalp or rectangular array. So here, if you click this box, you're going to get the data displayed in a rectangular array. So these are all the channels in no particular order, well, in the particular order that they're in, but not by location. So you can get a quick feeling for what the ERPs look like across the channels. You can also use the same menu display to do it on a scalp. So just unclick the rectangular array, and that gives you the same ERPs now arranged over the scalp. So you can see, where in the head these things were happening. Another option is to look at ERPs with scalp maps. So this is the interface. You can choose the time limits. NaN here in the second line, that's just asking for the highest RMS deviation. So it's usually the highest ERP in your chosen time frame there. You can also put in a millisecond time as well, or multiple millisecond times. So this is what that looks like, an example of that. So it's only choosing one time point to plot. You can choose multiple. All of these colored traces, those are different channels. And this line, this vertical line here at 352 milliseconds, that's showing you where on the head each of these values was occurring. So up here at the top, around 20 microvolts, those values were happening back here in the back of the head where it's most red. Down here, the lowest values, that was happening at these lower eye channels up here. And so if I had chosen, instead of NaN, if I had said 600, I would get a line here, and I would find out what the scalp map looked like at 600 milliseconds. And I could put 200, 400, 600, multiple time points as well. And the way that you can do that in a systematic way is to go to the ERP map series, and in 2D, you can step through the data in whatever interval you want. So here it's starting at 25 milliseconds and it's stepping through by 25 millisecond increments up to 300 milliseconds. So that looks like this. So you can see that when right after your event, there wasn't, on average, a lot of potential anywhere on the scalp there, and there wasn't a really clear scalp map. Then around 125 milliseconds after your stimulus, you get a pretty clear scalp map on average, and with higher amplitude of potential. And then you can see how that scalp map changes over time after your event of interest. And if you want to look really fancy in your publications and stuff, we can also do this in 3D, which is exactly the same information, just over a head model. If you click on any one of these, you can get one, and you can turn the head around and see more clearly what was happening in different parts of the head. Okay, so now we'll do some practical exercises. So this is very simple. Basically, just play with the functions that I've talked about. So you can follow this exactly, or you can skip things that aren't, relevant for you. If you're good on the basics, like I said, the rejection tools are good to play around with if you haven't done that before. We're going to take a break at 3 o'clock, so you have 25 minutes to play around with that. There's helpers around, so just raise your hand if you have a question, and somebody will come over and help. Yeah.
In the early step, when you high-pass filter the continuous data, you're still not running the ICA until after you've epochs the data.
So ICA can be run on epoch or continuous data. And so it's just dependent on how you pre-process data. I'm going to show in the next lecture how to reject continuous data and run ICA after that. In practice, I actually epoch first because it's easier to run the auto rejection, but ICA doesn't care. It doesn't even know the order of the data. Okay.